All right, let's jump right in. In today's manufacturing world, the goal is pretty simple on the surface, but it's actually incredibly tough. You have to make thousands, sometimes millions, of parts that are all perfectly identical. So how on earth do you achieve that kind of perfection at scale?
Well, here's the thing. Even with the most advanced, high-tech machines you can imagine, no two parts are ever truly the same. Seriously, there are always these tiny, microscopic differences. Engineers call it operational scatter between every single part that rolls off the line. And that, right there, is the million-dollar question, isn't it? If every single process has this invisible, random variation baked into it, how are you supposed to measure it? How do you get it under control? How can you possibly guarantee that every part is exactly what it's supposed to be? To figure that out, we have to give our opponent a name. Now, we're not talking about huge mistakes or a machine breaking down. We're talking about something much more subtle, the small, natural ups and downs in any process. This is what's known as inherent process variation.
Just think about it for a second. A cutting tool wears down by just a micron. The temperature in the factory changes by half a degree. A motor vibrates just a little bit differently than it did a minute ago. Each one of these tiny events introduces variation. And when you're making thousands of parts, that variation becomes this hidden enemy of quality that leads to defects, waste, and, you guessed it, huge business risks.
So, how do you fight an enemy you can't even see? Well, we use statistics. But don't worry, don't tune out. We're going to make this super simple with a fantastic analogy that everyone can understand: parking a car.
The tool we use is called process capability, or CPK for short. Now, the official definition sounds a little academic, but the idea behind it is actually really simple. CPK is just a measure of how well your process fits inside the lines, the design tolerances you're given. It's one single number that tells you if you've got plenty of wiggle room or if you're about to have a really bad day.
Okay, this is where it all clicks into place. Imagine your manufacturing process is a driver, and the design tolerance is a garage. A good driver, that's a process with a high CPK, parks the car perfectly in the middle every single time. They've got tons of space on both sides. But an unsteady driver, a low CPK process, is all over the place. Sure, they might get it right sometimes, but they are getting dangerously close to scraping the walls. CPK basically tells you which kind of driver you're dealing with. So what's the magic number? What are we aiming for here? Well, the gold standard in the industry is a CPK of 2.00. Reaching a CPK of 2 means your process is so stable, your driver is so good, that it only uses up half of the available space in the garage. You've built in this huge safety buffer, which makes producing a bad part incredibly unlikely.
And look, this isn't just some number for engineers to obsess over in a lab. This single metric has a massive, direct impact on a company's bottom line. We are talking millions and millions of dollars.
I just love this quote because it really cuts right to the chase. Companies that master their process capability don't just make less scrap. No, they fundamentally improve how their product performs in the real world, and they save an unbelievable amount of money in the process.
And here is the proof. Check this out. An automotive transmission manufacturer really focused on cranking up their CPK. And the result? A mind-blowing 75% drop in warranty complaints. It's simple. Fewer defects in the factory meant better products on the road and way happier customers. But, just as we were starting to get really good at this, a new challenge popped up. And it came from the very thing that was supposed to solve all our problems: automation.
Say hello to the CIM cell. This is a true marvel of modern engineering. You've got robots, CNC machines, and computers all linked together in one seamless, automated production line. The idea is to slash process time and boost production by taking human hands out of the equation.
But here's the crazy paradox. In these super-connected systems, that tiny bit of variation from step 1, it doesn't just go away. It gets passed down the line to step 2, which then adds its own little bit of variation. This is what's known as compounding variation, and it can actually make the final product less consistent than before, which tanks your overall process capability.
So just like that, the game changed. It wasn't enough anymore to just measure variation after the fact. The new frontier, the new goal, became to predict it and stop it before it could even happen. This is a huge shift in thinking. For decades, quality control was reactive. You'd make a big batch of parts, and then you'd inspect them to find the bad ones. The future is predictive. By analyzing data in real time, you can see a process starting to drift out of spec and fix it before a single bad part is ever made.
And this is how it's being done right now. Modern CNC machines are being loaded up with all kinds of sophisticated sensors. And these aren't just for show, they are constantly collecting data on everything, from temperature and vibration to the forces being exerted during the actual cutting process.
All of that data, this absolute fire hose of information, gets fed directly into machine learning models. These are smart algorithms that can spot subtle patterns that tell them an error is about to happen. For instance, it can predict when heat from the motor is going to cause a tiny warp in the part, and then it automatically tells the machine to adjust its movements to compensate for it.
And what you're seeing here is the incredible result. That blue line shows the natural thermal error, that variation just creeping into the process over time. But the green line? That shows the exact same process with this real-time compensation switched on. The machine is literally predicting its own future mistakes and correcting for them on the fly, keeping the process unbelievably stable.
So just how precise are we talking here? Well, real-world tests have confirmed that this kind of predictive system can crush those thermal errors down to less than 10 micrometers. To put that into perspective, that is smaller than the width of a single human red blood cell. It's a level of precision that was pure science fiction just a few years ago.
Which brings us to one final fascinating thought. We started this whole journey by just trying to measure and control these invisible variations. We've now reached a point where machines can predict and prevent their own mistakes in real time. So it really makes you wonder, what does manufacturing even look like when the very concept of a defect becomes a thing of the past?